Welcome. Hopf conjectured in 1932 that every positive curvature 2D dimensional manifold, Riemannian manifold, has positive Euler characteristic. It's an open problem still. I'm sure every geometer has thought about this problem, like every number theorist has thought about the Goldbach conjecture. It's one of the catchy conjectures which everybody can kind of, intuitively grasp, but there is a difficulty with this notion of sectional curvature. Positive sectional curvature doesn't relate with the Gauss-Bonnet-Chern curvature. So in dimension 2, of course, it's the same. In dimension 4, it's possible to derive this, as one has already, Chern or Milnor have already seen that in dimension 6 there is already there are already cases where the Gauss-Bonnet-Chern curvature is negative in some places, so you cannot directly argue, with the curvature. Another very beautiful conjecture is that there is on the 4 manifold S2 cross S2, there's a Riemannian metric with positive curvature. Also, this is wide open. And a third great problem in geometry, differential geometry, is the problem of classifying positive curvature manifolds, even dimensional positive curvature manifolds. It's like with finite simple groups, we have a list, but it's unlike in the group case, one has a classification. Here one just has a conjectured classification. And so there are the standard manifolds which come from the division algebras, and then there are exceptional cases like the Wallach and Eschenberg manifolds. So I worked once on this for a summer, had fun during the pandemic, and kind of saw kind of a curious relation between these positive curvature manifolds and bosons in physics. Probably an accident, but it's still kind of an interesting quest to make the standard model of particle physics, which is kind of a little bit weird, right? Why do we have these vector bosons? Why do we have the Higgs boson? Why do we have photons, gluon? Why do we have these structures? So for some cases we can look at the division algebras. I mean, there is a classification of division algebras, right? The real, the complex, the quaternions and the octonions. And then really we have here also kind of, we see this positive, we see this reflected in the positive curvature manifolds, and that the octonions are related with gravity somehow. That has been, thrown out at one point by Atiyah. So it's an old kind of attempt to make sense of the, make sense of particle physics by looking at the division algebras. But this is kind of a neat list, and we don't know whether this is the complete list or not. So I'm interested in discrete cases, so I'm kind of want to, of course, understand these conjectures from an experimental point of view, or kind of when you look at finite cases, you want to see what is going on. And so for me, manifold is just a discrete manifold graph, finite simple graph, such that every unit sphere is a sphere. So in this case, this is an example of a 2 manifold, and it has it's not a positive curvature with a naive definition of curvature. This Mickey Mouse curvature is actually due to Eberhard, a blind mathematician who kind of first came up with it. And so in 2 dimensions, the curvature is just 1 minus the number of neighbors divided by 6. So if you have 6 neighbors, then it's 0. So in this case, what do we have? I counted it. Actually, I labeled them with things. So we have 5, which have 4 neighbors. So this is 5 times curvature 1/3. And then we have 4, which have curvature 1/6, and then there are 2 with curvature minus 1, 6, and then the rest have zero curvature, flat points. And if you add them all up, all these curvatures, then you get 2. That's the Gauss-Bonnet result, which has been known since Eberhard. I mean, Eberhard did much more. He was looking which possible curvatures can occur. And so it's an interesting and old theme, but especially in higher dimensions. In higher dimensions, we want to have a good notion also of sectional curvature, which is a little bit problematic at first. So I once proved this in 2019. I proved this Mickey Mouse theorem. I call it Mickey Mouse theorem because I gave a talk in Baltimore about mathematics in general, and kind of took this as an example problem. And so the example problem is to classify all D manifolds which have the property that every embedded wheel graph has positive curvature, meaning 5 or less, 5 or 4 boundary spheres. So these are positive curvature cases. This is 0, this is negative curvature. So here, this example here, this is a point of negative curvature because there are 7 neighbors. Curvature is -1, 6. So, but it's a very naive and actually bad definition of sectional curvature, because take a manifold, and when you have in general, when you look at a manifold, you look at the neighbors, right? When you, like this is kind of a beautiful manifold here, 2 manifold. If you look at so let's assume this is the unit sphere in a 3-dimensional manifold. So what you have is, if you have a unit sphere, and then you look at all, you look at the center is connected to everything around it, and then if you look at a wheel graph, there are lots and lots of lots. So this is lots of negative curvature. Of course, there will be also lots of positive curvature, but negative curvature is just kind of, occurs. Also, when you do barycentric refinement, you get lots and lots of negative curvature. So you need a more flexible notion of curvature, and of course you want to have something like Riemannian metric on a discrete space. Now what you could do is kind of change the metric here, change the distances between points, but that's actually pretty lame and cannot be mathematically accessed very well. So much better, what I found actually also kind of during the pandemic, is to look at the index expectation, both in the continuum and the discrete index expectation curvature. So it's actually based on a very simple idea that Poincaré Hopf, you take a Morse function on a manifold, so there are indices, finitely many indices, you add up all these indices, critical points, finitely many critical points, add up all the indices, you get the Euler characteristic. So it's somehow like the curvature is on these particles, like on these, points, finitely many points. Now if you average, if you take a probability measure on all Morse functions, of course you get also a Gauss-Bonnet. If you take a probability measure such by Fubini, you get also Gauss-Bonnet is true, but you have much more flexibility. So you can change your probability measure. And one way to do that, you can, for example, place this in a Euclidean space and then take functions coming from the ambient space. And these functions, most of these functions are actually, Morse functions, and then look at the expectation, and that gives you the curvature. So for a polyhedron, of course the curvature will be located on the vertices. But if you take a nice smooth manifold, what you get is a continuous distribution, curvature distribution. Now, if you look at the notion of sectional curvature, you can also make sense of this, but by just taking, you take a point, and then you choose a 2-dimensional plane, let the geodesics move, you get a part of a small surface, and you compute the curvature of this surface, and what you get is the sectional curvature. So also that sectional curvatures can be accessed using this index expectation. It's actually easier than in the classical way. You compute the metric tensor, then you compute the gammas, there's the Christoffel symbols, you compute the Riemann tensor. Total mess if you do it, even if you can do it with a computer and see in the simplest cases the formulas are insane. So this gives you a more flexible notion of what positive curvature is, and in the discrete this is now accessible to experiments. So that's why I like that. I can take a 4 manifold or 6 manifold and I can study everything. I can study the Gauss-Bonnet-Chern curvature, which is just this curvature I talked about last time. What happens if you take a probability measure on every simplex, which tells you how much is assigned to each of the vertices, and so this energy of each simplex goes to the vertices, and once it settles to the vertices, that's what curvature is. But you have a lot of choice to distribute that, and these are parameters. So nowadays, in the time of AI, actually dumb AI, where you have everything in weights, you have billions or trillions of weights, which you generate with a random dumb algorithm, but it's actually very powerful, extremely powerful, but it's essentially just generating lots and lots and lots of things, and then you look at the best possible cases. It's like generating random ideas and then see which one is the best. It's actually a very dumb intelligence, but it's powerful, and it's based on single and multivariable calculus ideas. So I talked a lot in single variable calculus about this sigmoid function, which is a function which is smooth but which you can use to train networks. And actually what happens here, if you look at the situation, you have all these weights. For every of the weights you can compute curvatures, you can compute the Gauss-Bonnet-Chern curvature, which I also compute the sectional curvatures, and then you have a possibility to experimentally figure out what happens with these sectional curvatures. So what you can try is take a discrete S2 cross S2, maybe large enough so that you have a big enough amount of weights, and then try out until kind of minimize this. See how you can get to a situation where all the curvatures are positive. So if this is possible, it's maybe very complicated, right? You have a metric on S2 cross S2, which is very, very complicated. Maybe it's possible to do that and get that's one of the Hopf conjectures, right? One of the Hopf conjectures is whether there is a metric on S2 cross S2 which has positive curvature. The standard metric, product metric, of course, has flat situations. When you take a vector here and a vector here, you take the plane, so this is flat, so there is no positive curvature in general, but maybe it's possible to do it. It's a beautiful problem. Also, this is a beautiful problem. Also, this is a beautiful problem. I think this is one of the most beautiful problems in differential geometry, these conjectures, and I'm sure everybody has, secretly thought about this problem for a very, very long time. So I myself, of course, have thought about this for many years, and I've tried myself at one point with finding a curvature which is built up from sectional curvatures only. And so one of these, that's kind of one of the approaches. You want to find an index expectation measure, a curvature which is positive. If you find an index expectation curvature which is positive, for example for that conjecture here, then of course, because Gauss-Bonnet works, then you have positive Euler characteristic. So that's the idea. It doesn't work for the standard curvature, which is kind of the uniform way when you put it throw it in a Euclidean space, and you take the Haar measure on the sphere as your probability measure. That gives you the Gauss-Bonnet-Chern measure and curvature, and that is in general negative for 6 or higher dimensional manifold, negative some places. So it's an interesting kind of place to experiment, and I just talked about this now so that I don't forget. I kind of rewarm this from time to time. Maybe at one point I will kind of try whether I can use kind of some machine learning thing to actually get to good metric or good index expectation measures. That's it for today.